Hello everyone, this is Guanghan Zhao. Today I'm here to present our work, FunType, Intention Inferring Fan-Shaped Sum Interface for Text Entry on Small XR Keyboards. First, about our research background. We had an imagination of future life with AR devices in our daily life. And instead of those physical smartphones and tablets, we use virtual ones powered by those AR devices. And then we need to seamlessly transfer users' familiar typing habit into those virtual mid-air keyboards. And it can help us in daily lives, like using it in trains or air cabins. However, although the virtual space is indeed infinite, but unfortunately, the physical space we are living in is not. So therefore, we need to develop some special method to interact with those small virtual interfaces. Typing with such small virtual keyboards may cause fat finger error, which is more severe in mid-air input context than inputting using those touchscreens. To solve such problem, we aimed to develop a secondary UI that can be merged into a natural type behavior for disambiguation. So as we all know, when we tap on a touch screen, we will lift up our thumbs and then tap again. And that's where we place FunType to do the disambiguation. Okay, next, about the design of our fan-shaped interface. So we applied a 110 degrees layout aligned with SUM's natural rotational range around the CMC joint. And we set the radius of the fan to 61 millimeters to match the average SUM ridge. And those sector buttons placed on the outer edge for easier SUM tip selection. In addition, our layout strategies are: we always include a central sector for fast selection of the most likely candidate, and I will explain what's the most likely candidate later. And we apply asymmetric layout when there is even number of candidates to preserve the center position. And this will help the users to always have one button in the middle to select, and it can fast up the speed. And the user interface always auto-rotate after each touch, aligning with the SUM while staying parallel to the keyboard for easy access. Next, about our intention inferring mechanism. In short, we model the systematic bias between the user's touch point and the intended key, as we can see from the figure. And we use an EMA smoothing method to estimate a stable bias vector and infer the user's likely target position. And those candidate keys are ranked by distance-based confidence. Then we add a negative feedback loop to update the bias estimate whenever the inferred key does not match the user's actual choice, and we apply a dynamic trust level. It is updated using a sigmoid function of consecutive hits or fails. And the trust level controls the floating distance of the fan-shaped interface, moving it closer when reliable and faster when unreliable. As we can see from this video, if the user is continuously clicking or selecting on the first candidate, then the system will believe that it's inferring the correct intention from the user and move further to the keyboard. If not, it will move farther from the keyboard to leave additional space and time for the user to select the button they want. After implementing our prototype, we move on to pilot study, aimed to define which size is small enough for public usages. And we applied 4 different sizes from large to small and compared them in 2 different scenarios, including a standing scenario and a sitting scenario. Moreover, we not only collect the feedback from the user, but also those people sitting or standing next to him or her to collect feedbacks. And as a result, we found that the small size is the best size. Then we move on to the main experiment. We recruited 22 participants, and the task is to input text. We compared these 3 different methods and evaluate them. The results of the evaluation show that both Poke and FunType significantly improved typing speed over the baseline, and Poke was the fastest. And also, both methods also reduced error rates, and our method delivered the best overall accuracy. Both methods lowered workload, and our methods further reduced hand movement and arm fatigue. Beside the main experiment, we also applied a stress test. We noticed that while virtual model matches physical dimensions, it feels smaller than expected in XR, making interactions more difficult. As we can see from the video, this is exactly the same size of keyboard on Apple smartphone. And we noticed that other input methods like the baseline touch 1 and also the poke method are almost unusable on such a really compact keyboard. Therefore, we only conduct this stress test on FunType. The results we got from the stress test revealed that the capacity of FunType was, of course, reduced, but remained functional, and it can still be robust and accurate. So that's all. Thank you for listening.